Hi, Physics 2. Mr. Janowski here with the second part of, I'm sorry, not the second part, the next part of the chapters 15 and 16 slides. So the do know questions. First, what is the correspondence principle? So this is the idea that the predictions of special relativity correspond to the predictions of classical mechanics at speeds much lower than the speed of light. So why is this important? For hundreds of years after the time of Newton, we had tested Newton's ideas, and they seemed very, very accurate. They were making very, very good predictions. So when Einstein comes along with his different theory, well, it had to agree with Newton's ideas, at least in the realm of speeds much lower than the speed of light. So, yeah, that's the correspondence principle. Who measures proper length? To measure proper length, the observer, the person doing the measurements, has to be at rest relative to both points that are being measured. So the person who has proper time is the person who is present at both events, physically there at both events. The person who measures proper length is the one who is at rest relative to the length being measured. And what's the formula for length contraction? Yeah, it's this guy. L, observed length, is equal to L naught, proper length, times the ugliness term, square root of 1 minus v squared over c squared. So, yeah, today we are going to learn about E equals mc squared. So again, Einstein had those four amazing papers in his miracle year, 1905. So far, we've been talking about the third paper, which was special relativity. And then the fourth paper, the one on the equivalence of mass and energy, that was really just an afterthought to the third paper. About 2 months after he published the third paper, he published another one saying, oh, yeah, I've thought more about this, and I realized that if my ideas about special relativity are true, well, then energy is equal to mass times the speed of light squared. So, yeah, that's what this is. So we all know this, E equals mc squared. Technically, this is a little annoying. When you're doing these problems, it's more correct to write it this way. E naught equals m naught times c squared, where the naughts in this case mean rest energy is equal to rest mass times the speed of light squared. So E equals mc squared is only true if you're dealing with things that aren't moving in your frame of reference. If they're moving and if they have velocity, you have to use a slightly different formula. But I don't know. This is the more correct one to use. As long as the thing's not moving, just write it this way. It's just much prettier this way. That's the one everyone knows. So what does this mean? E equals mc squared. Well, remember, c is a very big number. The speed of light is a very high velocity, 3 times 10 to the 8th meters per second. If you take a very big number and you square it, you get a very, very big number. So c squared is equal to 9 times 10 to the 16th meters squared per second squared. So yeah, here it is written out. A 9 with 16 zeros after it, meters squared, second squared. So what this means is even very small amounts of mass will contain a lot of energy. So even if m is a very tiny amount of mass, because you're multiplying it by such a huge number, you're going to get a lot of energy out of it. And so where do we see this in use? So yeah, think back to chemistry. And if you're dealing with helium, almost all helium is helium-4, meaning it has 2 protons and 2 neutrons. All helium has 2 protons. That's what makes it helium. There is some amount of helium-3, but almost all of it is helium-4. So we know the mass of a proton very well, and we know the mass of a neutron very well. And if a helium-4 is 2 protons and 2 neutrons, that means if you do this, so twice the mass of a proton plus twice the mass of a neutron, you get this mass. So this is what we would naively expect a helium nucleus to have the mass of. I wanted to say weigh, but mass and weight aren't the same thing. You know that from Physics 1. But anyhow, the actual mass of a helium nucleus is a slightly different number. Yeah, it's hard to see the difference, but the actual mass is this one, the one that we're subtracting, 6.64 times 10 to the minus 27th. So it's a difference of 5 parts out of 669. So it's a small difference. But yeah, it's a very measurable difference. There is mass that has gone missing. So where did that mass go? Well, for the most part, it's sunlight. So this is what the sun does. This is where sunlight comes from. So this is what's called the proton-proton chain. And we don't really need to go into it in detail here. If you're taking astronomy, we'll go into it in detail there a little bit. But basically, what the sun does in its core, and it's been doing it for 5 billion years, and it will continue doing it for another 5 billion years. What the sun does is it takes 4 protons, a bunch of stuff happens, and it ends up with 2 protons and 2 neutrons. And the mass that you have down here at the bottom is very slightly less than the mass that you have up here at the top. And the mass that has gone missing is sunlight. So, yeah, that's where it goes. That's what the sun is doing. So the sun is not on fire. That's what people used to think up until basically Einstein had this idea. This is how we started to know what the sun really is. The sun is actually an ongoing nuclear explosion. So, yeah, it's kind of crazy. And I don't want this video to get too long, but I am going to wax a little philosophical here. So, yeah, the sun does this in its core, turns, this amount of mass into a slightly smaller amount of mass, and the mass that has gone missing becomes the sunlight. So, all right, briefly, it takes about 200,000 years. There's some debate on exactly how long for the light that is created when this happens to bounce its way all around the entire interior of the sun. It keeps getting absorbed and re-emitted and things like that. To get to the surface, then it takes another 8 minutes to get from the surface to the Earth. And then what's it going to do when it hits the Earth? Well, it might do photosynthesis. So this is the sunlight that, combines with carbon dioxide and water to let the plant turn it into glucose and oxygen. You get oxygen as a kind of waste product of that, and we appreciate the oxygen too. But yeah, it becomes glucose. And then if you're a herbivore, a vegetarian, you might eat that plant. If you are an omnivore, you might let some other animal eat that plant, and then you will eat that animal. So yeah, that energy ultimately it becomes you in many cases. So yeah, crazy. Practical applications of this stuff on Earth. Yeah, getting large amounts of energy from small amounts of mass allows for nuclear weapons, shown here, nuclear power, and nuclear submarines. So, yeah, that's what these guys are doing. They're turning some amount of mass into a slightly smaller amount of mass and using the energy that's released to do different things. Sometimes destructive things, but sometimes constructive things. Onto this idea, matter and antimatter. So for every elementary particle, there is a corresponding antimatter particle with the identical mass, but the opposite charge. So elementary particles. Electrons are elementary particles. So this is the mass of an electron, and this is the charge of an electron. In chemistry, you probably just called it, E minus for the charge of the electron, but Q is our symbol for charge. This is minus 1.60 times 10 to the minus 19th coulombs. That's the charge of an electron. Well, there is an anti-electron, and we use it so much that we gave it its own name. We don't typically call it an anti-electron. We call it a positron, which has exactly the same mass as an electron, only it has a positive charge. And so when these things get together, if you combine the electron with the positron, they annihilate. So all of this mass, the mass of the electron plus the mass of the positron, goes away, and you're left with the energy of that. You plug that amount of mass into E equals mc squared, and that's how much energy you get out of this. So yeah, again, electrons are elementary particles. You can't divide an electron into smaller pieces. Things like protons and neutrons are not elementary. Protons and neutrons are made of quarks. So, for example, a proton is 2 up quarks and a down quark. Well, there's an antiproton that instead of being made of 2 ups and a down is made of 2 anti-ups and 1 anti-down. And that's, an antiproton. There are also antineutrons too, and antineutrinos. It's weird. So I often wonder, I don't know how much this is true, but I feel like if you haven't studied this stuff yet, when you hear the word antimatter, you're going to assume that this is just some sci-fi nonsense, or at the best, maybe this is just really theoretical stuff, but we haven't found a use for it yet. And that's not true at all. We use antimatter every day. Antimatter is used in hospitals all of the time. So a PET scan, I don't know if you've ever had a PET scan. I never have, but maybe somebody has had a PET scan. A positron emission tomography scan. So positrons are being emitted. Tomography, I'm not positive, but I'm pretty sure tomography basically means making a 3-dimensional map. Topography would be a 2-dimensional map. I think tomography is a 3-dimensional map. I should have looked that up. But anyhow, during a PET scan, the patient is injected with a solution containing a glucose-like molecule containing a radioactive isotope. So it is a glucose-like molecule. So yeah, back to photosynthesis makes the glucose. Your body and your cells use a lot of glucose, and especially the cells in your brain. Your brain is very metabolically expensive. Your brain uses a lot of energy. Um, Other parts do too, of course, but your brain uses a lot. It takes a lot of calories to power your brain. So your brain uses a lot of glucose. So what they do is they make this thing that is like glucose, and your body will treat it like glucose, but we're basically fooling it, and we're sneaking something else in there. So this glucose-like molecule contains a radioactive isotope. So yeah, this is injected into your arm. So yeah, they make this stuff, they put it in a solution, they inject it into your arm, it goes into your bloodstream, and it goes to where it's needed most, and to a large degree, that's in your brain. So this isotope undergoes radioactive decay. It has a half-life of about 2 hours. So every time it decays, it releases a positron. So this positron flies out of this molecule. It collides with an electron that was just in your brain. You know, your brain is made of ordinary stuff. So protons, neutrons, and electrons. So there's plenty of electrons in your brain. So the positron is going to hit, the positron that is emitted here is going to just collide with an electron. These guys will annihilate. And the result of this particular annihilation is the production of two gamma rays. So this is a Greek letter gamma. This is a lowercase gamma. Gamma rays of equal energy shooting off in opposite directions. So, yeah, you've been injected with this stuff, you, the patient. So now you're in the PET machine. So the positron gets emitted, collides with an electron, produces two gamma rays. So now these gamma rays, which are very high energy photons, these are more high energy than X-rays even, they're going to shoot out from inside of your brain and in opposite directions, and the photons, the gamma rays, are going to be detected by this network of detectors all over the place. So they shoot out in opposite directions, so it's going to hit detectors on either side. And these detectors are synced up enough that the machine knows which one got there first, and it measures the time difference between when it arrived at each one, and that can figure out, using that, it can figure out exactly where the gamma rays were produced inside of your brain. And it can use that, and it makes an image of your brain. So then we watched this video, which, talks about why we have nuclear reactors, not nuclear reactors. We have particle accelerators in the basements of hospitals. And the basic reason is to make this stuff that has a half-life of 2 hours, you have to make it and use it almost right away. You can't make it and ship it and then store it and do things like that because this stuff just decays so quickly that it's not any good to you after a certain amount of time. So they make this stuff on site in any large hospitals, maybe not any large hospital, but many large hospitals will have this. A particle accelerator in the basement where they make this stuff, they prepare it, and then they send it upstairs and they inject it into patients who go into the PET machine. Just a few hours after the stuff was created, and then they make the images. And so these images here, these are PET scans of different people's brains. The first one is normal, just a perfectly healthy brain here. The middle one, mild cognitive impairment. And the last one is somebody with Alzheimer's disease. So you can see, because you have so many fewer gamma rays being produced, what that's telling you is that the glucose isn't being taken up in these regions here in this person's brain because of their Alzheimer's disease. Basically, that part of their brain isn't working. So, yeah, interesting. I'll put a link to this video in the description of my own video. Because medical physics, that's a field that some of you might be interested in the future. And that's as far as we got. So we learned E equals MC squared and some of the practical applications of that stuff. And hopefully you found this video helpful.